Hello everyone, welcome to Module 4, Lesson 2 of Mastering Ethereum. In today's lecture, we will explore the core architecture and functionality of Ethereum Virtual Machine, which is a key component that powers the Ethereum blockchain, and understand how the EVM executes smart contract, manages gas, and optimizes performance for decentralized applications. So let's get started. In the previous lecture, we had discussed about EVM architecture. Now let's dig deeper into this topic. The EVM is a core component that powers the Ethereum blockchain. It is powerful, Turing-complete virtual machine responsible for executing Ethereum smart contracts. The EVM provides secure, distributed, and decentralized environment for running these contracts, ensuring their deterministic execution and maintaining the integrity of Ethereum network. By understanding the EVM's architecture and functionality, developers can optimize their smart contract performance and minimize gas usage, essential for building efficient and cost-effective decentralized applications. At a higher level, the EVM manages the execution of Ethereum transactions, maintains the global state of Ethereum network, and manages the life cycle of Ethereum accounts and smart contracts. In the following slides, we will delve deeper into the key components of EVM, its instruction, and see how it interacts with broader Ethereum ecosystem. The Ethereum virtual machine consists of several components that work together to execute smart contracts on the Ethereum network. These include the execution context, the instruction set, the world state, the stack, memory, and storage. Each of these components would be discussed in detail in the following slides. The execution context. The execution context of the Ethereum virtual machine includes several key components that work together to execute smart contracts. The program counter keeps track of the current instructions being executed, guiding the flow of contracts logic. The stack is a last in first out data structure used for temporary storage of values and intermediate results during execution. LIFO or last in first out is a method for managing data in which the last item added is the first one to be removed. The memory provides a linear volatile space for storing temporary data needed by the contract. Finally, the available gas tracks the remaining computational resources, ensuring the deterministic and efficient execution of smart contract. The first key feature of the execution context is the program counter. The program counter or PC is a critical component of EVM that controls the flow of execution. It keeps a track of the current instructions being executed, ensuring the instructions are processed in the correct order. By monitoring the PC, the EVM can maintain the deterministic and sequential execution of smart contract logic, a key feature for ensuring the integrity and reliability of Ethereum network. The PC operates by pointing to the next instruction to be executed, advancing through the contract's code as execution progresses. This allows the EVM to move through the smart contract's logic step by step, updating the world state and stack accordingly. The program counter is essential for managing the control flow and order of operations within the EVM, supporting the deterministic and predictable execution of Ethereum transactions. Secondly, the EVM stack. The EVM utilizes a stack data structure for intermediate computations during execution of smart contracts. The stack operates on last in, first out principle, where the most recently pushed in item is the first to be popped off. The EVM stack is crucial for managing the flow of execution and performing complex operations, as it allows the virtual machine to store and retrieve values as needed through the contract's logic. Due to limited size of EVM stack, efficiently managing stack operations is essential for optimizing smart contract performance. Developers must carefully plan their contract's logic to minimize unnecessary stack push and pop operations, which can quickly consume the available stack space and lead out of the gas exception. By understanding the stack's role and limitations within the EVM, developers can write more efficient and cost-effective Ethereum smart contracts. The third component of execution context is EVM memory. In the Ethereum virtual machine, memory is linear, expandable array used for temporary data storage during contract execution. Unlike storage, which is persistent, memory is cleared after each transaction. Developers can access memory by specifying byte offsets and lengths, allowing them to read and write as needed throughout the contract's logic. The EVM memory is crucial component for smart contract execution. as it provides a dynamic workplace for storing intermediate values and performing complex computations. By leveraging memory, contracts can efficiently manipulate data without the need for persistent storage, which can be more costly in terms of gas usage. Careful management of memory, access, and sizing is essential for optimizing the performance and cost effectiveness of Ethereum dApps. Unlike memory, which is temporary, EVM uses a persistent key value store known as storage to maintain the state of smart contracts. Each contract has its own dedicated storage space, which allows it to store and retrieve critical data that persists between transactions. Unlike the volatile memory used for temporary computations, storage operations are more expensive in terms of gas consumption, making it important for developers to carefully optimize their usage. Smart contract state variables such as account balances, user information, and other critical data are typically stored in contracts' persistent storage. By leveraging storage, Ethereum dApps can maintain the necessary state information to function correctly, even across multiple transactions. However, developers must be mindful of cost associated with storage operations and strive to minimize unnecessary storage writes to optimize the overall gas efficiency of their contracts. The EVM is powered by a comprehensive instruction set consisting of 140 unique opcodes. These opcodes represent a wide range of low-level operations such as arithmetic, logical, stack, environmental, and control flow instructions. Mastering this instruction set is crucial for smart contract developers as it allows them to precisely control the execution of their contract's logic and optimize for performance and gas efficiency. Arithmetic opcodes. These are basic mathematical operations like addition, subtraction, multiplication, and division. Logical opcodes. These provide bitwise operations such as AND, OR, XOR, and NOT. Stack opcodes manage the EVM stack data structure, allowing for storage and retrieval of intermediate values. Environmental opcodes interact with the broader Ethereum ecosystem, accessing information about the current transaction block or account. Control flow opcodes facilitate branching and looping, enabling the execution of conditional statements and iterative logic. Opcodes can be thought of operators which are available in various programming languages that perform certain operations. Here are some examples of common opcodes. Push 1, which is a stack opcode, is an opcode that pushes a single byte value into the EVM stack, providing a simple way to load constant values for use in computations. Pop removes the top item from the stack, allowing developers to discard values no longer needed. This is also an example of stack opcode. Add. It adds the two topmost values on the stack, a fundamental arithmetic operation. This is an example of an arithmetic opcode. And jump sets the program counter to a new location, enabling control flow and conditional logic within the smart contract. Each of these opcode consumes a significant amount of gas, which developers must consider when optimizing the performance and efficiency of their Ethereum applications. Let us look into the third major component of EVM architecture, world state and accounts. The world state represents global state of all accounts on the Ethereum blockchain. It is stored in modified Merkle Patricia trie, a specialized data structure that enables efficient lookups and updates. There are two primary types of accounts on the Ethereum network: externally owned accounts or EOAs and contract accounts. EOAs are controlled by private keys and are typically used by individual users to hold and transfer Ether, the native cryptocurrency of Ethereum. In contrast, contract accounts are controlled by smart contract code which can be executed to perform a wide range of automated tasks, from token management to decentralized finance applications. Let's look into EOAs and contract accounts in much detail. EOAs or externally owned accounts are fundamental components of Ethereum blockchain. Unlike contract accounts which are controlled by smart contract code, EOAs are controlled by private keys. These private keys provide the sole means of authenticating transactions initiated by the EOA. EOAs can send transactions to other accounts including contract accounts, but they do not contain any executable code themselves. They simply serve as a repository for holding and transferring the Ether cryptocurrency within Ethereum ecosystem. We shall further see how EOAs and contract accounts interact with each other. The simplicity of EOA is a key design feature of Ethereum network. By separating user controlled accounts from contract controlled accounts, the system maintains a clear separation of concerns and promotes security by limiting the attack surface. EOS can be easily managed by individual users and do not require the complexity of deploying and interacting with smart contracts. In contrast to EOS, contract accounts on Ethereum network are controlled by their own smart contract code. These accounts have the ability to execute codes in response to transactions they receive, enabling the creation of decentralized applications on Ethereum platform. Contract accounts maintain their own persistent storage, allowing them to retain critical state information across multiple transactions. This storage can be used to store account balances, user data, and other essential information required for contracts functionality. By leveraging this storage, contract accounts can perform complex automated tasks and facilitate a wide range of decentralized services from token management to decentralized finance applications. Let us understand EOAs and contract accounts through this example. Imagine Ethereum as a bustling city. EOAs are individual citizens who can initiate transactions such as making payments or signing documents. Each citizen has a wallet, which is balance, and a unique ID, which is address, and they perform actions by themselves, which is through private keys. Contract accounts, on the other hand, are like businesses or automated service providers. They don't initiate actions on their own, but react to interactions. These businesses have rules, which is the smart contract code, that dictates how they respond to customer requests, which are the transactions. Once set up, they operate automatically based on their predefined rules, ensuring consistent and predictable service. The interaction between EOAs and contract accounts on the Ethereum network is facilitated through use of transactions. An EOA, which is controlled by a private key, can send a transaction to contract account, which is governed by its own smart contract code. This transaction then triggers the execution of contract's logic, allowing the contract account to update its stored state or even call functions in other contracts. For example, an EOA may send a transaction to decentralized finance contract, instructing it to transfer a certain amount of tokens. The contract's code would then execute, verifying the request, updating the token balances, and potentially interacting with other contracts to complete the transaction. This seamless interaction between user controlled accounts and contract control accounts is a fundamental aspect of Ethereum's design, enabling creation of complex decentralized applications on the platform. In the EVM, it is crucial to understand the difference between memory and storage. Memory is a volatile, temporary workspace used for holding data during transaction execution. It is cleared after each transaction, making it suitable for holding intermediate values and performing complex computations. In contrast, storage is a persistent key value store that maintains the long-term state of smart contracts, such as account balances, user data, and other critical information. While memory operations are relatively inexpensive in terms of gas consumption, storage operations are costly. This is because storage writes require updating the Ethereum blockchain's world state, which is fundamental part of network's secure and decentralized architecture. Developers must carefully optimize their usage of storage to ensure their Ethereum dApps are gas efficient and cost effective for users. Think of EVM as a computer. Memory in the EVM is like computer's RAM. It's a temporary fast access workspace used to hold data while program is running. When the program stops, all data in the memory is erased. Storage in the EVM is akin to computer's hard drive. It's permanent storage space where data is saved and persists even when the program stops. Accessing and writing to the storage is slower and more expensive compared to memory, but the data remains available for future use. The Ethereum virtual machine executes various operations, each with its own unique gas cost. Understanding these gas costs is crucial for writing efficient smart contracts. For example, remember in the previous lecture we had discussed about opcodes store and sload. Let us now discuss how they differ in gas cost. Store opcode is much more expensive than sload. Similarly, basic arithmetic operations like add and mul are relatively cheap compared to more complex computations. By knowing these gas costs of different EVM operations, Developers can optimize their smart contract code to minimize gas usage and ensure cost efficiency of users interacting with their decentralized application. To optimize gas storage in Ethereum smart contracts, developers should aim to minimize expensive operations like storage writes, instead utilize more cost-efficient memory for temporary calculations and only write to persistent storage when absolutely necessary. Some optimizing gas usage strategies include minimizing storage writes. Storage operations such as S-store opcode are generally more expensive than memory operations. Optimize contract logic to write to storage only when required, reducing the overall gas cost. Leverage memory. Use the volatile memory space for intermediate calculations and temporary data storage. Memory operations like mload and mstore are more cheaper than storage writes. Optimize contract structure. Design smart contract in a way that minimizes the number of storage updates required. This may involve techniques like batching multiple updates into a single transaction or using memory-based caching strategies. Here are some practical tips for gas optimization. Avoid unnecessary updates to contracts persistent storage, as storage writes are some of the most expensive operations in EVM. When writing loops in your smart contracts, be mindful of the number of iterations to avoid excessive gas consumption. Look for opportunities to break out of loop early or batch multiple updates together to reduce the overall gas cost. Leverage EVM-friendly data structures like mappings to store and access data efficiently. Mappings allow for constant time lookups, which can be more gas efficient than iterating through arrays or other complex data structures. When possible, consider batching multiple user requests or state updates into single transaction. This can significantly reduce the overall gas cost per operation as the fixed overhead of the transaction is amortized across multiple changes. In conclusion, understanding the architecture and functionality of Ethereum virtual machine is essential for developing optimized smart contracts. By comprehending how the EVM executes instructions and manages resources, developers can write more efficient code and significantly reduce gas cost for users interacting with their decentralized applications. The key insights gained from exploring the EVM's component such as program counter, stack, memory, and storage as well as its instruction set can help programmers make informed decisions when designing their smart contracts. Leveraging this knowledge to minimize expensive storage operations and strategically utilize the more cost-efficient memory can lead to substantial gas savings and better user experience for Ethereum DApp users. This brings us to the end of our lecture. Hope everyone is active and listening. Understanding the EVM's extensive instruction set is crucial for optimizing smart contract performance. By familiarizing yourself with gas cost of various individual opcodes, you can make informed decisions about which operation to use and how to structure your contract logic to minimize expensive storage writes. For example, leveraging memory-based calculations instead of storage updates or batching multiple state changes into a single transaction can lead to significant gas savings for your users. Another effective strategy for reducing the number of storage writes is to carefully examine your contract's data management approach. Utilize efficient data structures like mappings that allow for constant time lookups. Additionally, consider splitting your contract's functionality into multiple smaller contracts, each responsible for a specific set of tasks to further optimize gas usage. If any one of you has any questions, please post them on our Discord server for further discussions. Thank you for spending your precious time.